The evolution of wireless networks has always been defined by speed, but as we look toward the sixth generation, or 6G, the paradigm is shifting dramatically. As the demand for ubiquitous connectivity and high-precision awareness grows, we are moving beyond simple data transmission toward a world of integrated intelligence. Imagine a smart city where the infrastructure doesn't just route data, but actively perceives it, where every surface contributes to a high-precision, real-time awareness of the world. This is the vision of ubiquitous connectivity paired with environmental sensing. It is a world where digital and physical realities merge seamlessly, enabling autonomous systems to thrive. To achieve this, the industry is turning to a groundbreaking philosophy: integrated sensing and communication, commonly known as ISAC. Historically, radar for sensing and wireless networks for communication operated in silos. They used different frequency bands, different hardware, and completely separate signal processing protocols. ISAC shatters this division. It proposes that both sensing the environment and communicating data can coexist simultaneously, using the exact same spectral resources and infrastructure. By integrating these two functionalities, we eliminate redundancy. The same radio wave that transmits a video stream can simultaneously bounce off a vehicle to measure its speed and location. This duality unlocks superior spectral efficiency, saving valuable bandwidth. It also drives down energy consumption and cost, making advanced applications like digital twins a practical reality. But realizing the true potential of ISAC requires immense spatial degrees of freedom. We need the ability to steer signals with pinpoint accuracy in multiple directions at once. For years, the multi-input, multi-output, or MIMO architecture has been the gold standard. By using multiple antennas, MIMO systems exploit spatial dimensions to boost network capacity. As demands grow, so does the size of these arrays. But scaling up to ultramassive MIMO introduces severe, non-trivial challenges for integrated sensing and communication systems. Traditional massive MIMO relies on dedicated radio frequency chains for each antenna. These RF chains are packed with power-hungry components like amplifiers, phase shifters, and complex microstrip lines. When you multiply these components by hundreds or thousands of antennas, the power consumption skyrockets. The physical hardware becomes bulky, expensive, and incredibly inefficient to cool. These structural limitations create a formidable barrier. In energy-constrained scenarios or budget-conscious deployments, scaling traditional MIMO is simply no longer a viable path forward. In the search for a breakthrough, a compelling alternative has surfaced: intelligent metasurface-enabled transceiver design. This represents a radical departure from classical phased array antennas. An intelligent metasurface, or IM, is a remarkably thin, programmable structure. It is composed of numerous low-power, artificial meta-elements arranged on a specialized two-dimensional plane. These meta-elements are engineered at the sub-wavelength scale. This means their size and spacing are smaller than the wavelength of the electromagnetic signals they are designed to manipulate. Because of this microscopic precision, an intelligent metasurface can directly manipulate the amplitude and phase of an electromagnetic wave, acting almost like a programmable digital mirror. This effectively bypasses the need for massive, power-hungry RF chains. The metasurface performs the complex signal combining and pre-coding entirely in the wave domain. The world of intelligent metasurfaces is highly diverse, with several distinct architectures leading the charge. Let's explore the four primary designs driving this revolution. The most structurally simple and widely adopted is the Reconfigurable Intelligent Surface, or RIS. A typical RIS transceiver consists of just a feed antenna and a programmable planar surface. The feed antenna acts as a simple source, emitting a basic, unmodulated carrier wave. The magic happens when this wave strikes the Reconfigurable Intelligent Surface. The RIS elements dynamically adjust their electromagnetic responses over time. By rapidly shifting their states, they can imprint information directly onto the reflected carrier wave. This time-varying reflection generates multiple frequency harmonics. Each harmonic can be independently shaped and steered, allowing the RIS to perform dual-function communication and sensing from a single RF chain. While RIS is elegant in its simplicity, some applications demand even greater spatial degrees of freedom. This brings us to stacked intelligent metasurfaces, known as SIM. A SIM architecture utilizes multiple transmissive layers. As the initial signal passes through the first layer, a cascading coupling effect begins, creating a dense, highly interconnected transmission path. You can think of a SIM as a physical, wave-domain neural network. Signal processing occurs sequentially as the signal traverses the entire multi-layer structure. The phase shifts at each layer reconfigure the wavefront, synthesizing highly complex and tailored beam patterns that provide unparalleled control over the electromagnetic environment. Moving beyond externally fed structures, we encounter dynamic metasurface antennas, or DMAs. This is a novel concept within the paradigm of radiative metasurfaces. Unlike RIS or SIM, a DMA integrates the signal processing directly into the radiating structure itself. Independent signal streams are fed directly into these waveguides in parallel. As the signal travels down the line, it sequentially interacts with each embedded meta-element, which reconfigures and radiates the signal into the wireless channel. This manipulation is governed by a Lorentzian hardware constraint, meaning the radiated amplitude is intrinsically coupled to its phase shift. Yet, through collective control, DMAs synthesize precise concurrent beams. The fourth major architecture is the reconfigurable holographic surface, or RHS. Structurally, it shares similarities with the DMA, using an embedded parallel plate waveguide. However, the underlying physics are entirely different. Instead of resonance tuning, the RHS controls the local leakage rate, the radiated amplitude, along the waveguide structure. The RHS draws its inspiration from optical holography. The guided wave traveling inside the waveguide acts as a reference wave, while the desired beam pattern serves as the object wave. By regulating the voltage applied to each element, the RHS dynamically alters its amplitude profile. This creates a holographic pattern that perfectly reconstructs the desired electromagnetic wavefront. We have RIS, SIM, DMA, and RHS. Each architecture possesses unique wave manipulation mechanisms, distinct hardware constraints, and entirely different physical configurations. To systematically optimize integrated sensing and communication networks, we cannot treat these technologies in isolation. We need a unified analytical framework. This unified framework conceptually disaggregates the transmitter's behavior into three sequential functional slices: baseband processing, RF feeding, and reconfiguration. The first slice is baseband processing. This stage handles the input data streams before they reach the physical antennas, mapping data to enable spatial multiplexing. The second slice is the RF feeding matrix. This is the crucial bridge that characterizes how signals travel from the RF chains to the actual meta-elements. For embedded waveguides like DMA, this matrix reflects a serial topology. For externally fed systems like RIS, it models the complex free space wave propagation. The final slice is the reconfiguration matrix. This captures the metasurface's ability to actively alter the wavefront by applying element-wise phase or amplitude modifications. This matrix encapsulates the specific hardware constraints. An RIS is typically constrained to unit modulus phase changes, while an RHS is restricted to amplitude-only variations. In multi-layer systems like the SIM, the feeding and reconfiguration matrices operate as cascaded pairs, perfectly representing the sequential signal processing at every single layer. Together, these three slices form a comprehensive mathematical foundation. They unlock our ability to optimize the entire ISAC system, regardless of the underlying physical architecture. With our framework established, we must address the key technological hurdles. The first major hurdle is channel modeling for extremely large-scale antenna arrays. These massive apertures fundamentally alter wave propagation. By extending the Rayleigh distance, users and targets often fall into the radiative near-field region. In the near field, waves propagate as curves, spherical waves rather than flat planes. This introduces a nonlinear phase component based on the exact distance to the target. While mathematically complex, spherical wave modeling allows us to pinpoint and distinguish targets that are at the exact same angle but different distances, enabling unprecedented sensing precision. To handle the continuous, sub-wavelength nature of these apertures, we expand the spatial Green's function into the wave number domain, revealing the channel's true degrees of freedom. Once we understand the channel mathematically, we must estimate it in real time. Channel estimation for metasurfaces is a notoriously difficult, underdetermined problem. Imagine trying to infer the behavior of thousands of individual passive elements while only having access to a handful of active RF chains. Conventional pilot overheads would be prohibitive. To solve this, researchers are developing novel, hardware-tailored estimation algorithms. For example, applying unique phase configurations across layers over successive time slots. This allows the system to construct a diverse set of linear equations, accurately recovering the high-dimensional channel state from a severely limited set of observations. Armed with precise channel information, the system must execute beamforming. In an ISAC system, this is the art of balancing communication throughput with the sharpest possible sensing accuracy. This optimization is heavily dictated by hardware constraints. A strategy designed for the amplitude-only control of an RHS will fail entirely on a phase-only RIS. For cascaded architectures like SIM, beamforming is incredibly intricate. The phase shifts of all elements across all layers are strongly coupled in the wave domain. Optimizing a SIM requires advanced gradient-based methods to collectively tune thousands of parameters, orchestrating the wave's path to perfectly serve both communication users and sensing targets. The final piece of the puzzle is integrated waveform design. While spatial beamforming directs the signal, waveform design sculpts the signal's core properties in time and frequency. By utilizing time-modulated arrays, the system can apply highly specific temporal patterns to the metasurface elements, essentially coding the wave as it reflects. This time-varying response mixes with the carrier signal, generating distinct frequency harmonics. The fundamental frequency is dedicated to high-speed communication. Meanwhile, the engineered harmonics can currently handle high-resolution radar sensing tasks. This software-defined approach ensures optimal sensing performance with minimal interference to the data stream. The convergence of intelligent metasurfaces and integrated sensing and communication is not just an incremental upgrade, it is a complete paradigm shift for wireless networks. We are moving from bulky, hardware-heavy, power-hungry systems to elegant, software-defined surfaces. These technologies offer a realistic path to ubiquitous, energy-efficient intelligence. As we continue to refine the unified framework and conquer the complex challenges of near-field modeling and high-dimensional beamforming, the true potential of 6G comes into focus. Imagine a world where every wall, every building, and every device acts as an intelligent node, seamlessly connecting us while simultaneously understanding the physical environment around us. The metasurface revolution is paving the way for a smarter, faster, and profoundly integrated future. It enables the applications that will define the next decade of human progress. The next era of wireless connectivity has officially begun. The boundaries between communicating data and sensing reality have dissolved entirely. As we step into this new frontier, the invisible waves that surround us will no longer just carry our voices. They will illuminate our world.